Hey everyone, Mr. Shatter here to take a look at learning about functions from derivatives. The objective of this video is to use the first derivative test to find extreme values of f of x. The information we learned in the previous section, using the derivative to find extreme values, is all the information we're going to need in this section. But what this section does is it gives it a more formal definition and calls it the first derivative test. So there's not much new information in this section, more just a reiteration of things we already knew, but giving it a more formal twist. All right, let's get started. Here's a picture of how a function's derivative can tell us information about the original function f of x. The first derivative test comes in a few different pieces. Piece number 1 says, at a critical point C, if f prime changes from positive to negative at C, then f has a local maximum value at C. Notice it gives two examples. One example of when the derivative is 0 and another example of when it's undefined, but still it's a local maximum. If f prime changes from negative to positive, then f has a local minimum at the value of C. Again, the two cases of when it's 0 and when it's undefined. Okay, we already knew this, but again, we're giving it a more formal definition, calling it the first derivative test. Another example, if f prime does not change sign at C, then f is not an extreme value. Okay, sorry, then f is not an extreme value at C, or f has no local extreme value at C. All right, so it goes positive, positive, negative, negative, then it's not actually an extreme value. I call this a faker. It's just a shack definition. At endpoints, we've talked about this in class, but on a left endpoint, if the function is decreasing afterwards, then we know we have some type of local maximum. And on our left endpoint, if the function increases, we have some type of local minimum. A right endpoint, if the right endpoint is here, and the function is decreasing all the way throughout, we have a minimum. And if I have a right endpoint here and the function is increasing up until I get to my endpoint, then I have a local maximum. Let's look at an example using the first derivative test. Notice the directions are different this time. It doesn't just say find the extrema. It says use the first derivative test to find local extreme values. Identify any that are absolute. Okay, so we're doing the same math that we were just doing in the previous section. This time it's just a little bit more formalized, okay? So if I want to do this, take a derivative. So the derivative is 3x squared minus 12. And if I want to say this thing is undefined, I couldn't come up with any x values, so it's never undefined. So if I want to set it equal to 0, I should probably factor it, so that'd be 3x squared minus 4, which means that, of course, you have the difference of squares here, minus 2 and plus 2, and so you get the roots of 2 and negative 2. 2 and negative 2 are the two things that make the derivative equal to 0. So we put them on a sign chart. This is the graph of the derivative we're testing these values at, and we do negative 2 and positive 2. And we test negative 100 billion, and negative 100 billion goes into the derivative, and out comes a super big positive. Plug in 0, you get negative 12 as an answer, so negative. And then you plug in a number like 100 billion, positive 100 billion, and you get a really big positive. And so what this tells us is that you have some type of maximum at negative 2 and some type of minimum at positive 2. The question is, are they absolute or locals? And we don't have any endpoints here, so we can't just assume that we can just test the y values. So instead we have to rely on our knowledge of the function. Well, let's think about this function for a moment. Here it is right here. X cubed minus 12x minus 5. This is a pretty simple polynomial, a cubic polynomial, and I know it has a positive leading coefficient. So without doing much more, I know that positive cubics will go up to positive infinity as x gets really big, and down to negative infinity as x gets really small. So because of that, I can assume that this graph has neither an absolute max nor an absolute min. All right? So these things that we found over here to the right are both locals, okay? So if we summarize our answer, we say that f of x has a local max of, if you plug negative 2 into the function, you get 11, so of 11 at x equals negative 2, and a local min of, if you plug 2 into the original, you get negative 21, of negative 21 at x equals positive 2, at x equals positive 2, okay? The question also says identify any absolute extrema. This function does not have any absolute extrema, so I could write an argument saying since the limit as x approaches positive infinity of f of x is infinity, and the limit as x approaches negative infinity of f of x equals negative infinity, f of x has no absolute extrema. Okay, so this would be a pretty sufficient argument that covers everything I needed.